In this video, we're going to be talking about cyclic forms of monosaccharides. The learning objective for this video is to convert from a Fischer projection into a Haworth projection. We learned in our aldehyde and ketone chapter 14, that when an alcohol adds to a aldehyde, then we form hemiacetals. And so in our carbohydrate molecules, we have both aldehydes and alcohols. And that means we can have an intramolecular reaction where the OH group of the molecule bends around and reacts with the aldehyde or ketone. In order to do this, you can see here that this is a simplified molecule. This is not a carbohydrate here, but if we count down the number of carbons, we have 1, 2, 3, 4, 5, and then the OH group is off of the 5th carbon. That means we're going to have 5 carbons and an oxygen in our ring. So this is 5C plus 1O makes a 6-membered ring. After that, it's a matter of mapping out what has happened. This carbon number 1 turns into a hemiacetal. Remember that hemiacetals have both an OH and an ether on the same carbon. And this is now a new chiral center, because you can see it has 1, 2, 3 groups and a 4th hydrogen not drawn. And so this new chiral center here. Every time we make a ring with our sugars, we will either be making 6-membered rings or 5-membered rings. We will never be making 7-membered rings, and we will never be making 4-membered rings. It's always going to be either 6 members or 5 members in our ring. Since we do form a new chiral center in our molecule, this is known as the anomeric carbon. This anomeric carbon can exist in we can either have what we call a beta form or an alpha form. And that beta and alpha is dependent on whether these OH groups and this back not chiral carbon are on the same side of the ring or on opposite sides of the ring. So beta means same side. I remember that because both of the bumps in beta have them on the same side. Alpha means that they cross one another. And so that means that they are across from one another. So if they're across from one another, then they are alpha. If they are on the same side of the ring, then they are beta. That holds true even if you have an L isomer. So for instance, in this last picture here, they are on the same side of the ring. It's not just a matter of whether this is going down or up. These are on the same side of the ring. They're both down, and that makes it the beta form. It's just the L isomers because this is down. So I'm going to write down for L. up for D. As we draw our Haworth projections from our Fischer projections, these are Haworth projections where it's drawn like a hexagon. And we have to remember that since this is a cyclo ring, it's not an aromatic ring. Aromatic rings are planar. Our cyclohexane rings are not planar. They are more shaped like a chair, but we are drawing them like hexagons for simplicity rather than weird chair things. It's not really flat though. As we draw our hexagons, we are going to rely heavily on mapping our carbons. The first step is to rotate your molecule horizontally. Just rotate it 90 degrees that way in order to lay it flat. And you can see our aldehyde goes from being here to our aldehyde on the right. Then you can number your carbons to keep track of them. The next step is to twist the chain around. Again, we are relying heavily on mapping here. If we just draw out a hexagon, we can know that if we are going to be reacting with this one, then we are going to have 5 carbons plus an OH. 5 carbons plus OH. Well, 5 carbons plus 1 O equals 6 members in our ring. And so that's going to result in a hexagon. And we always draw our hexagon like this with our OH in the back. We draw our hexagon kind of flat. This is carbon number 1, always. And carbon number 1 is always our aldehyde, or it's where the functional group is. So it's always where your aldehyde or your ketone was. And then you can draw from there. You really only have to pay attention to a few carbon locations here. This is, you're going to have to pay attention to 2, 3, and 4. After that, you don't have to pay as close of attention to the orientation of things. The alpha and beta can interchange. So this one you don't have to pay attention to because it will depend on whether it's alpha or beta. And this back one, you don't really have to pay attention to too much because all naturally occurring sugars are D, which means it's going to be up most of the time. But if it is an L, then it would be drawn down. After that, you just map your OHs. So you can see here that this is a number 2. This is number 2 here. So that's going to be down. This is up. And this is down. So I can redraw my molecule here, going down, up, down, and get my OHs on there. As we close the ring and form our new chiral center, this molecule can either form the beta or alpha form, and this ring can actually open back up and reform the other anomer. So these are known as anomers of one another. That means that they are kind of like isomers. They have the same chemical formula, but this location is the different orientation for the chiral center. So like D and L were enantiomers of one another. We have the alpha and beta are anomers of one another. And it can interchange. Let's draw both the alpha and the beta forms of D-mannose. Go ahead and pause the video and try to come up with something on your own, and then unpause the video when you're ready to look at how I'm going to do it. Okay, so we're going to be reacting with this OH group. It's the last chiral center OH. Six-membered rings are usually the most stable, and so if you can form a six-membered ring, then do it. So if this one's going to come up and it's going to attack there. We said the first thing to do was to lay this molecule flat. I'm just going to turn my head sideways so that I'm going to make all of these facing down. And those are going to face up. So we are going to have six-membered rings, and so I'm just going to draw a skeleton outline of everything. To draw my O first, apparently. Okay. As you draw your hexagons, it will take practice to get your hexagons. Next, I'm going to decide whether to draw this one up or down. This is the D isomer because it's on the right. That means that this will need to be going up. And so the three dots here say up. So since this was the D isomer, I'm going to draw that up along the back. I know I have to draw both the alpha form and the beta form. Alpha form means that this is going to be on the opposite side of the ring. Remember, alpha, you have to cross it. And so this will be the alpha form, and this will be the beta form. Now I have to pay attention to the orientation of my OH groups for carbons 2, 3, and 4. Just those three locations. I see a pattern on 2, 3, and 4 of up, up, down. So I'm going to go up, up, down, up, up, down, and draw my OHs. And there we go. We have completed our Haworth projections. You can finish them off if you want to by drawing in all of the H's to help you remember that they are there. Remember, we have formed a hemiacetal, and in the aldehyde and ketone chapter, we learned that you can form acetals. So we will be doing that soon. So as I mentioned earlier, this new anomeric carbon can open back up, as shown here, and then close again in the other orientation. This process of opening back up and closing again is known as mutarotation. They are in equilibrium with each other. Fructose, which is a ketose, can also form a cyclic structure. This is a picture showing how that's going to work. With our fructose, the ketone is at carbon number 2, and so that OH group comes and reacts with that location. We still draw it where it's on the right, and that's just the convention that happens, but you lose a member of your ring and end up forming a cyclic 5-membered ring with fructose. And so this is still where that last carbon in the chain is how you decide whether it's alpha, meaning across, or same side of the ring, meaning beta. Let's practice classifying this molecule. The structure is shown here, the Haworth structure here. Go ahead and pause the video and look at the structure and decide what it is. Okay, so I see this going up, and therefore it is D. And so I can cross out the L's. This OH group is on the same side. Same side means beta because I can draw a beta with bumps on both sides. And so this particular drawing is beta D galactose. Additional vocabulary that you may see thrown out on homework or on ACS exams or something is pyranose and furanose. Pyranose means six-membered ring, and furanose means five-membered ring. 5 starts with F, and so that's how I kind of remember it, although I don't have a great way of remembering pyranose. That's just kind of how they are. These are named after these the common names for these organic molecules respectively. Pyran has a 6-membered ring with an O in it, and furan has a 5-membered ring with an O in it.